Okay, so we're recording. Cool. So you might have seen, I did send a YouTube link to the video for those of you not on Canvas from last lecture, and we'll continue to do that. And then I put a bunch of stuff up on a Google Drive. Now, one of the challenges with that is I'm in the midst of redoing the course on a it's not really a website. It's a learning environment called Thinkific, and we're going to start offering some system dynamics courses to the general public, where you don't have to pay $5,000 per course on this site, this learning environment called Thinkific. Of course, you don't get university credit or anything. You can't get a master's degree or whatever. But a lot of people we find don't care about that. They want to learn how to do system dynamics rather than get, a degree or something. However, the original idea was to skew the Thinkific courses and what have you to economics and system dynamics, which is my thing, because we get a lot of economics people, and we'll get into that maybe even today a little bit about how economics intertwines with all this stuff. My point is, I put some of the stuff from the WP, or all of the stuff from the WPI version, but I might have some of the stuff from the Thinkific version, although a lot is the same. So there might not always be 100%. I might show something here, but it's not on the Google Drive. And if something is missing because of that, let me know, and it must be in the Thinkific version, and I'll upload it. So, because there's so many files and whatever, to try and keep everything exactly the same is a little bit of a challenge. And then I change my mind and stuff like that. But there's a lot of stuff up there for you guys. So, and the other caveat is some of it is still in Vensim. I've only recently switched to Stella. And because of that, I have hundreds of models and what have you in Vensim. And I haven't converted everything over yet. So some of the stuff uploaded will be in Vensim. But you know what? You can get a free version of Vensim PLE, Personal Learners Edition, and you can open them. And it's a lot of people in the world use Vensim and PowerSim and other things. So to see the same thing in a different software package is probably a good thing, too, because not everybody is going to work in Stella. And you come across their stuff and you have to be able to sort of figure out what people have done. Okay, so that's just updating you on that stuff. So having said that, let me share my screen, and here's our dynamic syllabus. Okay, so and this is for Ashley. The lecture is also here, right, for if you have access to Canvas, right? And what we're going to do today is more talk about the history of system dynamics, and along the way, see some famous models and put a lot of what we're going to do into context. So why do we, in the future, in the course, why are we going to do this? Why are we going to do that? Well, in light of the bigger picture, the bigger story, the bigger narrative, I think it's valuable, and people usually find it interesting to hear the story of the history of the field. And it's also good to know, I think, if one intends to work in system dynamics beyond taking a single course. If it's a one-off, you say, well, whatever, but if you work in the field, it's probably good to know a lot of the oral history and some of the gee whiz stories and some of the reasons why things are the way they are in our field. Okay. So having said that, let's go over here. That's from last time. We're going to clear that. There it is, a little bit of a delay. And let's talk about the history of our field. So our field was created by somebody named J.W. Forster. As I think everybody more or less knows. I first met Jay in 1983, and he passed away in 2016. So I knew him for quite a long time. I imagine that was 33 years or something like that, whatever that is. It's a quite a long time. And so I heard many of his lectures. I ate meals with him. I sat in his office and shot the bull and whatever. So when I say I think Jay would have said this, that, or the other, I probably have a fairly good idea of that what his thinking was about things, although I can't swear to it. So anyway, who is Jay Forrester? Well, he grew up on a cattle ranch in Nebraska. He was born in 1918. And his parents thought that he would be a cattle rancher because they were on a cattle ranch in Nebraska. And they thought he was eventually going to go to sort of agricultural school to learn how to breed horses and, whatever you got to learn to run a sort of a farm and a ranch. But when he was in high school, he noted that the family farm didn't have electricity. So he set upon himself the task of electrifying the family farm. And so he went to the dump and scrounged parts from old automobiles and whatever. And he built a windmill and a generator and electrified the family farm. So Jay's father said, well, we're planning on you going to agricultural school, but you might have a different path in life in light of you're a pretty smart kid. So they sent him to the University of Nebraska, and he took a Bachelor of Science degree in electrical engineering, which at the time was mostly power systems, electrical grid stuff. And his teachers there said, yeah, you're pretty good. So why don't we send you to graduate school? So he applied to, I should say, MIT. I believe he said he heard about the school because, remember, this is way back in the 1930s, because his mother, I think, had worked in Springfield, Massachusetts at one point in her life. So he heard about the school, so he applied, he got in, and he was assigned to work in Gordon Brown's servo mechanism lab. In fact, I'll put that in here. Gordon Brown's servo mechanism lab. So Gordon Brown was one of the fathers of servo mechanisms. He's not the father. He didn't invent a servo mechanism, but because the servos were invented kind of in the 1920s. And so, and by the way, when Jay got to, I should maybe use a pen here. When Jay got to MIT, it was 1939. Okay, and servos were invented like in the 20s. But Gordon Brown was still sort of on the cutting edge of this somewhat new area of servo mechanisms. What are servos? Servos are feedback systems. Okay, the easiest way to think about a servo mechanism is as a thermostat. Okay, what you do with a thermostat is set a goal or a target, right? A setting. I would like the room to maintain this temperature. And then if the actual temperature deviates from the desired temperature, the setting, either the air conditioning or the heat is kicked on, right? And the actual temperature is brought back in alignment with the goal. So, a cruise control on a car is the same thing. A guidance system on an aircraft or a missile would be servo mechanisms. Think about the human body. On average, most people, the set point is 98.6 degrees Fahrenheit. And again, if you go outside into the beastly heat, you perspire. The body is trying to cool it off. The servos in the body are trying to cool you off, get you back down to 98.6. And if you go outside in the freezing cold or jump in a cold river, Arkansas River, in your backyard, your house is sliding towards it, you shiver, right? The body's trying to warm you back up to 98.6, right? So a robot's arm, the desired position of the arm is over here. So the servos or the sensors pick it up and the servo motor moves it over and it grabs the whatever it's doing and on it goes. So servos are kind of everywhere in biological systems, in physical systems. And as soon as you say goal or target, well, humans have goals or targets for things, right? So as you can see, it's kind of a ubiquitous idea, even though the average citizen maybe doesn't think too deeply about feedback loops. John Sturman would always say, if you don't think the world is filled with feedback loops, try riding a bicycle and closing your eyes. So at any rate, so Jay is put into Gordon Brown's servo mechanism lab. And in 1939, if you're familiar with any world history, national tensions were rising. Hitler was doing his thing. The Japanese were doing their thing, on and on. And so war is on the horizon. So Gordon was primarily doing stuff for the Navy. And a lot of it involved radar and guns. So prior to the invention of servo mechanisms, ships had to rely on the skill of the gunner's mates to protect the ship. So here's the ship, you know, sailing through the water, right? And then here's a plane that's attacking it, you know, shooting at it. And then the gunner's mates had to try and defend the ship, and they had to learn how to lead the plane. You can't just aim right at it because by the time the shell gets there, the plane is gone and all that. Well, servo mechanisms and radar allowed the ship to lock on to the target and then automatically move the gun, quickly do the calculations and so forth. So they were developing that stuff, and it was quite primitive at the time. In fact, Jay said in Gordon's lab, we had to do everything with hydraulics because the Navy didn't trust electronics. So even though he was an electrical engineering student, he said he had to learn mechanical engineering to do what the Navy wanted. So Jay would tell a whole lot of stories about, and if you go to the ebook that is on, well, you're on the Canvas site, but if you go to the syllabus even, the ebook, it's on the System Dynamics Society site. I did it for the Department of Energy, and one of the chapters in the ebook is sort of Jay's history. And you'll even see there's the aircraft carrier Lexington. So he was sent out to Pearl Harbor to fix some of the radar and servos and whatever on the Lexington. And he wasn't finished. And the XO, he said, came up to him and said, "We're going out to sea, just so you know." And so Jay went out to sea with the aircraft carrier, and they got torpedoed and all sorts of crazy things. So exciting times. Jay gets back from all that stuff, and the war ends, and the Navy comes to him. Well, I think he came to Gordon, actually. Gordon was a very nice guy. He was an Australian guy, very sweet man. I knew him when he was older. So as a young man, I have no idea. But as an older guy, he was very, very sort of like grandpa-like and very kind to everybody and whatever. But so the Navy went to Gordon, I think, and said, "We have a project." And he gave it to Jay, I think, as I remember the story. And they said, "Look, we want to, we need a computer that pilots can use to simulate aircraft behavior, you know, to train in a simulator." Now, of course, that's aerospace engineering and whatever 101 today, pilot training 101 today. But in 1946, that was a new idea. And so Jay accepted the project, and they set to work on an analog computer. So analog computers work by measuring physical stuff like the physical movement of a gear, or the filling or draining of tanks of water, or the amount of current flowing through a wire. And if you've ever seen the movie The Imitation Game about Alan Turing, it stars Benedict Cumberbatch or Cumberbunch, whatever his name is. I don't know if you've ever seen that movie where Alan Turing cracks the Enigma code during World War II for the submarines, the Nazi submarines. Actually, he didn't crack the code, but some Polish mathematicians cracked it, but they needed a way when they're intercepting messages in real time to quickly decode them. And so he came up with the Enigma machine, or sorry, nothing, an analog computer to decode the messages. And if you see the movie, you'll see the movement of the gears. That's where how the calculations are made. Well, Jay found out that analog computers couldn't really do what the Navy wanted done. So they switched to this new area of digital computers. Okay. And they created a computer called Whirlwind 1. Okay. Which it wasn't the world's first digital computer, but it was MIT's first general purpose digital computer. And as Jay likes to say, it was the world's first general purpose digital computer that worked reliably.
What year was that, Mike?
1946, I believe.
46, okay.
Yeah. So Whirlwind still exists today. You can see some of it at the Computer Museum in Boston. And when Jay retired, at the time, he was born in 1918, so he was 70 in 1988. Yeah. And it was mandatory retirement at age 70 at that point. There was no ageism or whatever laws. So he had to retire. And I was invited to his retirement dinner in 1988. And it was held at the Computer Museum right next to Whirlwind.
That's pretty cool.
Part of Whirlwind. The other part of Whirlwind is at the Smithsonian Institution down in Washington. So if you see this figure here from our site, that's magnetic core storage, and Jay Forrester invented that. So what you see is these little donuts here, these little teeny cores, and then the wires wrapped around them. So when they would when you run an electric current through a piece of metal, even a nail, it'll generate a magnetic field, right? That's called an inductor in electronics, right? And so the little cores either were magnetized clockwise or counterclockwise. And that was the ones and zeros in the digital computer. And magnetic core storage, Jay holds the patent on that, the original patent. Others refined it later, but the original patent. And he received the Presidential Medal of Technology from George Bush Sr. at the White House for that invention. The side story that nobody knows is Mrs. Forrester, of course, accompanied him, Susan Forrester, to the ceremony, and she slipped on the newly waxed floor of the White House and broke her hip and had to be attended to by the White House physician. So,
oh my goodness.
Yeah, kind of a weird side story. So one time after Jay had retired, they moved him to a different office after he retired, which is very common at universities. And I go in to visit him, and I said, "Oh, Jay, you got some new artwork on your wall." He goes, "That's not artwork." And I go look up close. I thought it was kind of a modern art thing or something. And it was magnetic core storage. One of his former students had found somewhere and salvaged it and then mounted it on a mahogany board and with a plaque and stuff and sent it to him. And he was displaying it. And you had to look really close because those things are really small, those little cores. But magnetic core storage was how all digital computers configured their primary memory from the late 1940s to the early 1980s until basically the silicon chip days. And Jay would always joke that it took him 7 years to convince IBM that it was a good idea and they should use it in their computers. And in the 1960s, 7 years in court to convince IBM that they didn't think of it first. So Jay and MIT won the court case, and IBM apparently had to pay royalties to Jay and MIT for every computer they had built from 1940 whatever to that point in time. So it was a very large revenue raising patent.
Wow.
MIT, yeah. So there is a kind of an interesting clip, and I usually play this for people. And given that we have a lot of wiggle room in our schedule, I'm going to play it here for you. Some of you may remember Edward R. Murrow. He preceded Walter Cronkite as the anchor of the CBS Evening News. Okay, so and he made his bones by reporting from London during World War II. His radio broadcast would start with, "This is London." Not terribly exciting, but he was known for that. Anyway, after the war, in the early 1950s, he hosted a show on this somewhat new fandangle thing called television, called See It Now. And he brought CBS's cameras to Jay Forrester and Whirlwind. Okay, so here's the actual footage from that TV show, and hopefully, hopefully everybody can see it. And I have to stop the share, and I have to reshare, I think, and I have to say share sound so you can hear it. So let's see if this works.
With the new plants and additions now under construction, Alcoa's annual production will be raised to 1,300,000,000 pounds. 4 times as much as 1939. In this way, Alcoa continues to meet its responsibility as the leading producer of a vital metal, aluminum, by Alcoa, Aluminum Company of America.
These are days of mechanical and electronic marvels. The Massachusetts Institute of Technology has developed a new one for the Navy. It's a Whirlwind electronic computer. With considerable trepidation, we undertake to interview this new machine. Now to MIT and the computer lab at Cambridge, Massachusetts.
Hello, New York. Hello, New York. This is Cambridge. And this is the oscilloscope of the Whirlwind electronic computer.
I assume that, like any delicate, finely tuned piece of mechanism, this has a human element involved, too, has it?
Yes, Mr. Morrow. I am Jay Forrester, director of the Digital Computer Laboratory where Whirlwind was built.
Well, I wonder if we could take a look around, sir.
Yes, let's first look at one of the storage tubes, such as the Whirlwind uses for memory. Whirlwind stores in these tubes information in 25 millionths of a second. And further down the row, you can see some of the electronic circuits which make Whirlwind work. Would you like to try to use the machine?
Yes, of course, but I have an idea, Mr. Forrester. Since this computer was made in conjunction with the Office of Naval Research, why don't we switch down to the Pentagon in Washington and let the Navy's research chief, Admiral Bolster, give Whirlwind the workout. What's your problem, Admiral?
Well, Ed, this problem concerns the Navy's Viking rocket. This rocket goes up 135 miles into the sky. Now, at the standard rate of fuel consumption, I would like to see the computer trace the flight path of this rocket and see how it can determine at any instant, say at the end of 40 seconds, the amount of fuel remaining and the velocity at that instant. The rocket weighs 11,000 pounds at takeoff and carries an initial fuel load of 8,500 pounds.
All right, Mr. Forrester?
All right, Admiral Bolster, we'll see what we can do. Let's look at the oscilloscope where the problem has been set up. Over on the left-hand side, you will notice fuel consumption decreasing as the rocket takes off. And on the right-hand side, there's a scale that shows the rocket velocity. The rocket position is shown by the trajectory that you're now looking at. And as it reaches the peak of its trajectory, the velocity, you will notice, has dropped off to a minimum. Then as the rocket starts down, velocity picks up again toward a maximum velocity when the rocket hits the ground. How's that?
Well, how about that, Admiral?
Looks very good to me.
Well, sir, I'm just a middleman here. I didn't understand the question, and I don't understand the answer. But now let's go back to MIT for a moment. Are you there, Mr. Foster?
Yes, Mr. Morrow.
Well, let's try another problem on a little more personal level. Let's suppose that back in 1626, I had been an Indian, and I had received for the sale of Manhattan Island, say, $24. And if I'd been out covering a story for TB and then I'd invested that $24 at 6% interest back in 1626, what would I have today?
Well, that would be a good investment. To set up such a problem on the machine, we first have to prepare a control tape, something like this, where the information from the machine has been punched in. That tape is then read into the computer, as you can see over here, and fed into the storage tubes in the other room, where the information is remembered until the machine starts a solution of the problem. Now, the machine started the solution. We see here typing out the answers on a typewriter. From 1926 until 1951, your $24 would have grown to something like $4,027,727,000 and some odd cents. Do you think that would be a good investment?
Thank you, sir, very much indeed. Someday I'll ask you to figure out whether that is before or after taxes. Very fascinating, Mr. Foster.
Very good to have had you with us, Mr. Murrow. And before leaving, we would like to show you another kind of mathematical problem that some of the boys have worked out in their spare time in a less serious vein for Sunday afternoon.
Thank you very much indeed, Mr. Foster and the MIT lab. This next story is an American story, so American that it could only happen in Korea, Italy, Germany, France, anywhere in the world where American fighting men have gone.
That's hilarious.
Okay, so you can see that's what back in the day, that's what computing was like. One other point I'll make about Whirlwind is that one of the graduate students on the project was a guy by the name of Ken Olsen. Right? Does anybody know who Ken Olsen was?
I know the name, but I can't remember who he was.
He started Digital Equipment Corporation, DEC, and which was bought by Compaq, which was bought by Hewlett Packard, whatever. But he had Jay on the board of directors for Digital Equipment for 10 years or so, and they used System Dynamics to conceive of the growth of the company in its early years. Okay, we share again. We can continue. We push on here. So the military was pretty happy with the Whirlwind thing. So they came back to Jay and they said, we got another one for you. We'd like to have you head up, or really co-head up with Bob Everett, a project to create a network of Whirlwind computers hooked up to radar systems to protect the United States from incoming missiles and bombers and stuff like that. And so that became the SAGE air missile defense system for semi-automatic ground environment. And so Bob Everett and Jay co-directed that. And I don't know if they created Lincoln Laboratories to do that or if it already existed, but they did it at Lincoln Labs, which if you're familiar with the Boston area, it's right on the Beltway. It still exists. Jay liked to say that, well, that was the vacuum tube era. And if you know anything, if you're a little older, you remember vacuum tube TVs and radios in the old days, and those things would burn out constantly. And you'd open up the back and you'd look in there. I remember as a kid, and you try and figure out which one was burned out, because a lot of them would blacken from the filaments sort of burning inside. But just because it was blackened didn't mean it was burned out. So you picked the ones you thought might be candidates for the one that was burned out. And you'd go like to the grocery store, and there'd be a kiosk there, and you'd plug in one and you hit a switch, and if it lit up, no, that's okay. And you'd find the one that was burned out, and then they'd sell you a new one. Well, Jay said, when these damn vacuum tubes burned out, we just redesigned them so they wouldn't burn out. And the computers in the SAGE project were up and running from the early 1950s to the early 1980s, and they had an uptime of 99.7%. Okay. When SAGE was ready for commercialization to be moved out of Lincoln Laboratories, and I think IBM took it over at the time, Bob Everett stayed with the project and it was spun off from Lincoln Labs into MITRE Corporation. I don't know if anybody has ever heard of MITRE. MITRE Corporation is still around. And Forrester said, well, I thought I might make a servo mechanism company or something like that. And then Jack Killian, the president of MIT, said, whoa, 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 don't go running away yet. Is there anything we can do around here to interest you, to keep you at the university? And Jay thought about it, and he said, well, in his mind, the biggest impediment to human progress was not from physical systems, but from systems with people in them, social systems. Because when he was working on these big projects, he was working with a lot of contractors, IBM, Westinghouse, and all. And he said it's the people systems that make life difficult, right? Jay always
Really
liked
clear things up.
Jay always liked to paraphrase B.F. Skinner, who I guess said that if the ancient Greeks were magically transported to the present day, they would understand absolutely nothing about our technology, but they would understand absolutely everything about our social problems, because they're still here exactly as they were thousands of years ago. They haven't been solved. So I don't know, one thing led to another, and the idea was, well, why don't you go over, Jay, to our new business school at MIT and see if you can figure out something that would make corporations more successful. So the Sloan School of Management at MIT was created in 1950 by way of a grant from, or a gift from, Alfred Sloan, hence the name. And you may or may not know who Alfred Sloan was, but he was the head of General Motors, and he was the guy who came up with the notion of breaking General Motors up into Cadillac, Oldsmobile, Buick, Pontiac, Chevrolet, later Saturn, to diversify the market, segment the market, and control General Motors, this behemoth at the time corporation. So he was an engineer by training and wondered what a business school would look like growing up at a polytechnic rather than a traditional liberal arts university. And as Jay liked to say, he spent $10 million to run the experiment. So this is the mid-1950s now. And Jay went over to the business school, to Sloan. Let's call it I think it was 55. And he said, well, my first year, my obligation was to think. So Jay said he was assigned 3 graduate students who were economics majors, economics students. And he said after the first year, he dismissed them. He said they were good, nice people, but he said, we didn't think the same way. So in 56, he replaced them with 3 electrical engineering students. Ed Roberts, Will Fye, and Jack Pugh. And together, Jay and Ed and Will and Jack created System Dynamics. So Will Fye has passed away. He went on to be a professor of electrical engineering, I think electrical engineering at Georgia Tech. Ed Roberts is still, he's like 85. He's still at MIT, going in every day, still a professor there. And Jack Pugh is retired and living up in Maine. Jack is known for creating Dynamo, which was the second System Dynamics computer language, but the most dominant one for decades. The first System Dynamics software package was called Simple, which stood for Simulation of Industrial Management Problems with Lots of Equations. But Dynamo replaced Simple. And Dynamo was the dominant System Dynamics package from the late 1950s to the GUI, graphical user interface era of the 1980s, mid-1980s. Ed Roberts and Jack Pugh went on to found a consulting company called Pugh Roberts. And it's still around, but it's been bought out a couple of times. I don't know its current name. It's been recently bought out again. But they did and are still doing system dynamics management consulting. So when System Dynamics was first created by Forrester, he called it Industrial Dynamics, not System Dynamics. And in fact, the first book in our field was called Industrial Dynamics. It came out in 1961. And for many years, it was the Bible of system dynamics. Now it's Sturman's book, but Industrial Dynamics is still a great read. It is absolutely relevant today. And if you pick up a copy and take a look at it, it's really chock full of lots of good how to do it stuff, right? The first paper in the field of system dynamics, or, how do we date the beginning of our field? Well, oh, and by the way, look at here's stuff on Sage, a document about Sage, it's a website about Sage and a website about Whirlwind. The first, I should have it up here somewhere here. Oh yeah, the first system dynamics paper was this one here. This is the start. So when did system dynamics officially start as a field? November 5th, 1956, if you want to date it somewhere. So this was a paper that, remember, Jay's first year was spent thinking, right? Reviewing the literature, just wondering, what he could do to make corporations successful. And he said, I helped invent the computer. Oh, by the way, the reason Jay didn't get this one, Jay would always say this, the reason he didn't stay with computing in the early 1950s, he moved on to Sloan and all that, was he said he thought the pioneering days of the computer were over. He said when he used to go to computing conferences, everybody would know everybody. And he said he started to go by the mid 1950s, he'd go to computer conferences and he wouldn't know anybody and nobody knew him. So he decided that's time to move on to invent a new field. In fact, Jack Pugh would always tell the story that when Jack was graduating with his master's degree, after the ceremony, there was cookies and cake and coffee and stuff like that. And Jack's parents, this is in the 1950s, Jack's parents were there, right? And so they're chatting and having cookies and cake and all that. And Forrester wanders over. And Jack said, I was so embarrassed because my dad looked Forrester up and down like this and said, what do you do around here? Jack's father didn't know who the hell Forrester. And Jay always would pause when you'd ask him a question and the gears would turn. He was, and he said, well, I invent new fields. But that's exactly what he did, right? So what Jay said, so this is the first paper, but notice it says D-0. And some of Jay's students documented all of his memos, so that's D technically 0000. So Jay said, when we were inventing computing, we documented everything we did week by week. So there was a historical record of what we were doing. Since we were inventing a new field here, industrial dynamics, later system dynamics, we're going to document what we're doing here. So Jay said, we're going to have a D-memo series, which documents everything, good and bad, that we're finding out in our field. So the very first D-memo is D-0, the first paper in our field. If you know anything about Jay, you did not sleep on his shift. You produced excellence or get out. So D, I think it's 003. I think it's D003 or D005. I could look it up. Is a D memo on how to write a proper D memo. And you will write them this way. So David Anderson tells the story that he was driven nuts, but because in the old days when you did system dynamics on a mainframe, you would submit your job usually on punch cards, and it would go into a queue. Then it would go to the CPU and get processed, and it would go to a printer queue, and it come out on these big green sheets of paper. This is how I started doing it, and they'd tear it off and give you your output, and you'd page through it, these big sheets, and then you'd see your plots. And like population would be P, 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 and food would be F, 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 whatever. You could tell the symbol, but it would, and then what you'd have to do is take a pen and connect the dots so you could see the curves. So David Anderson said Forrester had a system dynamics pen, and he insisted you use a special pen to connect the dots or he wouldn't accept your output. So you wanted it done a certain way. So notice, because I'm an economist by training formally, and remember, he's thinking. He started working with some econ students. He's trying to figure out in a business school, how do we make corporations more successful and use a computer and use servo mechanisms and the stuff he knew to make corporations more successful. So he wondered, well, what do economists do in terms of economic modeling? Okay. So he says here, in our first paper, in the material that follows, I comment on model building from the viewpoint of its effectiveness in predicting economic behavior and its value as a guide to the management of industrial organizations and the establishment of operating policies and organizational structure. Okay. Although the text is written in a somewhat critical manner, I look on most of the statements as proposition. So he takes a shot at the economists and their modeling techniques of that era. And then he basically says, here's how you guys should be doing it. So the very first paper in our field is a shot at the economists and their modeling acumen or lack thereof. Now, notice it's to the faculty research seminar. So it was kind of an in-house thing to the economists and other business school types at MIT. But, those people are no slouches, but basically they ignored this memo. Okay, it was a shot from Jay to the economists, and the economists kind of ignored them. So we'll keep that idea in our hip pocket as we go along here. Okay, so by the way, later on, the name was changed from industrial dynamics to system dynamics when Jay broadened out past just modeling corporate structures. I once asked Jack Pugh, Jack, how did you change the name from industrial dynamics to system dynamics? He goes, Jesus, I don't remember. Go ask Dennis Meadows. So I asked Dennis, he goes, oh, I remember. He goes, one day we just came in and there was a memo in each of our mailboxes from Jay saying, you will now call our field system dynamics, not industrial dynamics. Do not use that phrase anymore. He's like, okay, now we're system dynamics. So throughout the late 1950s and most of the 1960s, Forrester and his group did corporate modeling. By the way, the very first system dynamics model was a hand simulation that Jay did. Jay did essentially what the computer does, but he did it by hand. It was for a General Electric plant in Kentucky that was having labor and inventory issues. Okay, but they did all corporate modeling. And Suzanne, I'll get to you in 1 second. So what would Jay do? He would go into companies and go around to the various departments and ask people, well, what do you do around here? You go to the marketing people and say, what do you do around here? You go to shop floor people, what do you do around here? And guess what? They can tell you, right? Because they do it every day, all day. So I always use the example, if you're in charge of pencils at Acme Company, and Jay said, what do you do around here? He said, well, I make sure all of our employees have pencils. And Jay would say, well, tell me more. Well, if somebody needs a pencil, I open my cupboard and I give them a pencil. And Jay would say, well, how many pencils do you have in your cupboard? Oh, I have 3 cases typically. Okay. How many pencils are in a case? And they could tell you. How do you know when you're running low on pencils? Oh, whatever. And then, well, how do you get more pencils? Well, I order them from wherever. How long does it take you to get pencils from whatever, Staples or whatever the thing was? Well, people can tell you all this. Well, guess what? You can write a system dynamics equation that captures all that. And what Jay would find out is that everywhere in the organization, At each point, people could tell you what they did, and what they were doing made complete sense. It was rational. They were getting well compensated for what they were doing. But when you hooked it all together, all the interactions of the rational stuff at each point caused the corporation's problems that you're being called in for. And Jay would do things like he would be called into a company on a Wednesday, and on Tuesday he would call up the company and pretend to be a customer and say, I'm interested in, XYZ part or whatever item, whatever SK unit, storekeeper unit. What does it cost? And they'd tell them, how long does it take to get it to me? And they would say, oh, we'll have it there by Friday. So Forrester would go in the next day to the company and say, what's your average delivery delay? And they'd say, oh, 2 weeks. They said, really? I just called in yesterday and they told me you'd have it to me by Friday. So a lot of times, there's what the sales force is quoting, and then there's what actually is. And when there's a discrepancy, there's pressures in the system and whatever. So yeah, so Suzanne, go ahead. What's your comment or question? Or
I've heard for a long time, years, about these D memos, and I never really understood what they were until you told me right now, but I'm super curious. Is D for like development, or where did that come from? Document.
So
Documents memo.
Yeah, documents or D memos.
For documentation of our process.
Yeah. So
Okay.
So when I first came to MIT to visit with those guys, and Jay, you'll see, has been fighting with the economists. He took the first shot, right? I got off the elevator and there was the door. It was like the Wizard of Oz when they get to the Emerald City and they knock and a little hatch opens up and, go away and all that. So the door opens and Sturman sticks his head out and he goes, yes. I said, I was a student, Mike Gradzicki, I'm an econ student. He goes, egad's an economist. Then he goes, we'll let you in anyway. And the door opens and I'm admitted into the sanctum. And Jay's office was way in the back in his conference room, but in the main area were all the administrative assistants and whatever. And along the walls were all the filing cabinets containing the D memos, because back in those days, they were typed out. And if you wanted one, you had to write to MIT and probably pay postage or something. And then they sent you the D memo. So they would have copies, multiple copies of each one. And the popular ones, they had a lot of copies. And the staff was always sending these things out and whatever. So today they're all PDF'd and whatever. And in fact, if I go, let's see over here, if I go, go, MIT SD collection. So now they're all PDF'd and organized and whatever, right? So, where's the D memo on, let's see.
They're at the System Dynamics Society too, aren't they? If they're all.
Yeah, you can get these from the society. Yeah. So it's D005 is standard numbering and filing system for memoranda originating in the industrial dynamics group. That's the D memo on how to write a proper D memo. Okay, so they're doing all the corporate stuff, right? And Jay's book, Industrial Dynamics, has this production distribution system as an example in it. It's got a retailer, a wholesaler, a distributor, and a factory, and it all interacts and all this. So Jay, in some sense, invented supply chain management. By the way, remember the first system dynamics model I said was a hand simulation that Jay did in Kentucky, right? Jay made a game out of his model from the Industrial Dynamics book. It's called the beer game. Has anybody ever heard of the beer game? Suzanne, now this is a board game. This is not what you do at the local tavern, right?
I facilitated it twice at Kansas State.
Okay, so you know the beer game. It's a very famous, it's a well-known game. And it has the same stuff that's in Jay's model in his book, Industrial Dynamics book. But it's a hand game and you're moving around. You used to move around pennies, now you move around bingo chips and and what have you. By the way, Ed Roberts, one of the graduate students that helped invent system dynamics, his doctoral dissertation was on project management. Why are there cost and scheduling overruns in projects? In some sense, system dynamics helped invent project management. So people don't realize this, but system dynamics has been at the cutting edge of a lot of stuff. So at any rate, most of the applications, certainly by Jay himself and his team, were corporate things throughout the late 1950s and 1960s. And they were trying to figure out how to do system dynamics properly, how to get the software going, how to teach it, whatever. Jay's original idea was that, well, once he gets it going, it'll be in every business school. You'd study accounting, management, marketing, finance, and system dynamics, because Jay always said there's probably on the order of 15 to 20 generic structures that would represent most situations that corporate managers would face. And if they would play with the simulations, they would get the intuition about the dynamics and be better managers. So all that changed a little bit, or expanded, I should say, in 1968. So there was a guy by the name of John Collins who became a professor of urban planning at MIT. And let's see if we can just, we'll see if we can find John here. So there he was. He was the former mayor of Boston. He was a two-time mayor of Boston. Very popular mayor. Okay. So in 1968, John Collins said, I'm not going to be mayor anymore. And MIT offered him I think it was just a one-year position as a professor of urban planning. So a lot of politicians, ambassadors, they go to the Kennedy School or whatever, and they teach for a year or two, very common. So John Collins, as a young man, had been stricken with polio. And he needed these hand cane things and sometimes a wheelchair, depending on how he was feeling, to get around. And in 1968, you didn't have the Americans with Disability Act or any of that stuff. So MIT was like, well, this guy's got to be able to get to an office somewhere. Like, how are we going to do this? So MIT had purchased, I think it was an old Palmolive soap building. It's building E240 at MIT. And at the time, it's gone now, but when I was out there visiting for a couple of years, it was there still. It was as a factory. It had a loading dock and a ramp, loading ramp, and a freight elevator. And they said, let's give them an office in that building. They rehabbed it from I think it was a soap factory into an office space. And they said, he can use the ramp to get up there and the freight elevator and whatever. So by chance, the office right next to Forrester had a prof who was on sabbatical and gone for the year. So they gave John Collins an office right next to Jay Forrester. So Collins asked Forrester, as a office neighbor, what do you do around here? Again, what do you do around here? And Forrester explained the corporate modeling. I talked to and Collins said, well, if you can model a corporation, can you model a city? And Jay said, well, yeah, in principle, but what I do, I talk to the marketing people, I talk to the accounting people, I talk to the finance people, I talk to the shop floor people, and I ask them what they do, and they can tell me. I write a question. He said, by analogy, I would have to talk to the police chief, the fire chief, the DPW people, the school board people, whatever. And Collins said, when do you want them here? And Jay said, I don't mean like once. I mean, they got to be here every Wednesday for at least half a day for a semester. Collins said, done. When do you want to start? Collins was so revered politically in Boston that he could make that happen. And so Jay said, okay, do it. And so Collins had these folks come in, and Jay did group model building. How does a city run? What problems are there in a city? And so forth. And Jay turned that into a system dynamics model and wrote it up in a book called Urban Dynamics. It came out in 1969 with a foreword by John Collins. Now, I think I have there's Urban Dynamics, System Dynamics in the news. So I have, so if we go, let's see, Changing Thinking, Crichton, Bray. Let's see, maybe I put it up here. So here's an interview with the guy who created, Will Wright, who created the game SimCity. So in the interview, so you wouldn't cite any other games that inspired SimCity? And he says, I'd say the biggest inspiration, if there had to be one, was the work of Jay Forrester, who's considered the father of system dynamics and one of the very first people to use a computer for simulation. When I started getting the idea for SimCity, I started going to the library and reading. He did a lot of his work back in the 50s, working with very primitive computers and very primitive models, but yeah, he was the first person to try and simulate a city, okay, and so forth. Okay. Again, a lot of people don't realize all the origins of stuff or things that have their origins in system dynamics. They don't realize it.
You know, it's really remarkable, Mike, and it just begs the question of why is it still such a struggle to try and introduce people to this way of problem solving?
The $64,000 question. The very first SD conference I went to was when we created the System Dynamics Society in 1983. And there was a panel of all the luminaries who sat up at the front and debated, why isn't system dynamics more popular? We're still debating it. It's one of those head scratchers. It's like, I don't know. Nobody knows exactly what the heck is the problem here because it's so useful. And for not every problem, you got, not every problem is a system dynamics problem. But when it is, it's very useful. Like, well, anyway, so what was remember, we model problems from a systems perspective. We don't model systems. So what was the problem? Well, the team, Collins, all the luminaries from Boston and Jay agreed that the problem was, or the question was, why are cities very popular at the beginning of their lifespan? Everybody wants to move there. So you see this shape, that's exponential growth. That means it's very powerful. The city's really growing, but at some point it hits an inflection point and growth starts to slow. But then guess what happens? A lot of cities, it goes like this. So cities are popular places to go and live and work and whatever. And at some point they become unpopular or attractive and unattractive. Okay, so why is that? That's like, why is that happening? And what do you do about it? That was the motivating question. Notice the book is called Urban Dynamics, not Boston Dynamics, because you'll see as we go along, one of the big ideas in system dynamics is that a good model is really a family of models. It's generic. So Jay always said you could take his urban dynamics model and tune it up for any city with the right parameters and table functions and stuff. Jack Homer did a model of the diffusion of medical technologies into the marketplace, and he did it first for cardiac pacemakers and then for the antibiotic clindamycin, very different medical technologies with very different time shapes. But the same model with just 5 changes, modest changes, could replicate both medical technologies. And it's been used to replicate other medical technologies as well. Okay, so a mark of a good system dynamics model is that it's a sort of a family of models or a generic structure. Okay, so so Jay wrote it up in a book called Urban Dynamics. John Collins wrote the introduction, but guess what? It was a very controversial book. Okay, now why? Well, among the things Jay tried to do was, or tried, I should say not try to do, but one of the things he tried was he ran or tested a lot of the policies that LBJ and his Great Society people were implementing. So if you remember LBJ, President Johnson, right, had his Great Society programs, and many of them were related to cities, right, urban areas. And so Jay said, well, let's try all of LBJ's, programs on the model. And he found that most of them did nothing or even made the city worse. Moreover, the thing that made the city better was counterintuitive and at first pass, horrible, mean, racist, all sorts of crazy things. Now, one of the problems, quotation fingers, with Jay's books is if you look at them, they're mainly equations and graphs. So most people see equations and graphs and run in the opposite direction. There's an old adage in the publishing business: for every equation you put in your book, you cut your readers in half. Why? People are not comfortable with math and they can't even read a graph, most people. So if you can read this graph, you are unusual in terms of humanity. Most people can't look at this and it's like, right? So Jay's books were all equations and graphs. And so right out of the box, it's hard to understand them, okay? But secondly, the whole counterintuitive things, people are not familiar with complex systems and their counterintuitive nature. And they certainly weren't that way in the 1960s. So the book was very, very controversial. And so let's take a look. So before we take a look, so one of the things that Jay's students did, and it was Lou Elfeld and Alan Graham, they said, wow, the Jay's book is so controversial here. And a big part of it is people don't understand what Jay is saying, and there's too many equations and graphs. So they wrote a book, I think it was 1974, I think. I got it on my shelf here. I could look it up, but I think it was 1974, called Introduction to Urban Dynamics. And what they said is, let's start with one stock and one flow, super simple, and let's add a little something to it, add a little something, and build up to a model such that then you could go read Jay's book and understand what he was doing. So in the book, it starts very simple, and they build Urban 1, and then they go to Urban 2. And once you have the Urban 2 model, you can jump off and read Jay's book. That was the idea. Okay. So what I did was I was goofing around. I programmed up Urban 2. I think it's pretty faithful. I might have tweaked it a little bit here and there just for giggles. I can't remember. I did this a while ago. I intend to turn this into a flight simulator. I just haven't gotten that far. But so this is the jump off point for being able to understand urban dynamics. But up in the left-hand side here, we have our reference mode. Okay, so this is the data for the city of Boston, right? And then we've got red is Worcester, green is Springfield, and purple is Lowell. And you can see they all have the same characteristic shape. There's a little bit of a recovery in all cases, but there's the peak and the decline. And again, they're on the one scale here. If you were to do these other graphs on their own scale, you would see it would look a little more dramatic. You can manipulate the scales of graphs to make things look more dramatic or less dramatic, as the case may be. But at any rate, they all have that same characteristic shape as I showed you before. So that would be our reference mode. That's the problem. Why do you have this peak and then collapse? Popular place to be, then an unpopular place to be. Okay, so remember last time I fit a model to data by twirling the little knob? right? And I had an exogenous where there was just data, and then I had endogenous, and then I twirled the knob and the two curves. So I manually fit the model to the data. And I said we could have an algorithm within Stella fit the model to the data if we wanted to, but there was no need. It was easy to twirl. So when you want your model to replicate or mimic or look like the reference mode, you can say qualitatively it has that same shape, but it doesn't match point by point very well. Or, yeah, I want to take the time to literally match it tight to the data. And for this case, I didn't do that. I don't really have those numbers. I suppose I could hunt them down. I'm fairly certain I could find Boston population going back to 1790 or whatever it is. But no need. Qualitatively it matches. But what my point is, if you want more than a qualitative match, we can do that, right? But no need here. So let's take a quick look at what Jay was up to and what Lou and Alan were up to in terms of their simpler situation. So there's a demographic sector, and I kind of sectorized it. They didn't do this exactly in their book, but it's my sort of rendition of it. But if you look here, we have low-income population, we have middle-income population, and we have high-income or upper-income population. So right away, think about income inequality. If that's an issue that you wanted to look at, whether it's globally, between nations, or among nations, or within a nation, or within a state, or whatever, in a city, we could do that, right? Notice you can move, or people can move among the groups. And the way you do that primarily is with training or education. Okay, so if you get more skills, you can get a higher paying job. There is nothing in their model that has you reverting and going back to low income, but of course, a more sophisticated model. Again, we're always like, what can I leave out? What is the reference mode? What is the problem? And if situations in which high-income people become middle-income people or lose their fortunes or whatever is important to the story, then you want to have that in there. But if not, it's not important to the stories or the problem. So they didn't put that in there, but you could put it in if you wanted. Notice also there's 5 flows here. So in terms of people coming in, people make babies and they come in from elsewhere. They in-migrate to the city. They're attracted to the city. In terms of leaving, they die, they out-migrate, or they move into another income category. And of course, down here, there's only 4 because the upper income people can't get any richer, at least not in the model. Suzanne, you got your virtual hand up.
Yes. So this is your sectorization of the urban dynamics model?
Of the Urban 2 model from the Intro to Urban Dynamics book, yes.
So
in other words, they did it in Dynamo in 1974, and I didn't use modern software and the techniques to reproduce it, but I chunked it the way Stella would allow me to, and Dynamo back then did not allow you to chunk it category.
And one of the this was a big learning point for me today that I don't know why it never landed before, but it did today, is that the hallmark of a really good model is that it can be reused not for just one city, but multiple cities, similar situations with minor modifications. And so this particular model, would it be possible to use this same sort of framework as a starting place for a city, a township, or even a state, or an economic, say, sector of the United States? Can it go up and down a hierarchy and still be pretty much the same model?
Yeah, I think the answer is yes. And like demographers will tell you, in terms of in and out migration, for example, that it's very common in demographic modeling to have the out migration being just some fraction, but the fraction is bigger the more income that you have. Where's out migration? Because the more income you have, presumably the more skills you have, and then the more opportunities opportunities, you have to go elsewhere for a better job or whatever, or for family reasons or whatever, but you have the wherewithal to move, whereas the poor people don't. They're kind of trapped. So, but people are always leaving because for whatever laundry list of reasons, but the higher the income class, the higher fraction is leaving because they have more ability to move. On the other hand, coming in, it's a function of the attractiveness of the city or the region or the state or whatever. So if you have net out migration, it's because the people who are always leaving swamp the number of people who are coming in, or vice versa. So in other words, demographers, I've talked to demographers, and they've agreed that, yeah, that's a first cut, that's fine. That's kind of how we do it. You know, there can be more detailed models than this, but they said, yeah, it's a good way to model it. Birth rate, people make more people, very common, and you know, some fraction, there's an average lifespan or a fraction of the population who passes. So this wouldn't freak out. Well, when I've showed this sort of model to demographers in the past a couple of times, they were like, yeah, this is fine. I don't object to anything here. So yeah, you could use it for other populations. Ashley, you got your hand up.
Yeah, I just had a question as we're kind of going through the interdisciplinary nature of systems dynamics. This is much more on the public policy side. So there are a lot of really good public policy programs in the Massachusetts area, like the Kennedy Center at Harvard. Are any of them looking at this type of modeling in their public policy and public administration programs?
Certainly Brandeis does, because Brad Morrison is there. Kennedy School, I don't know. I know Peter Senge, a big SD guy, works with a bunch of people at the Kennedy School. Whether they're sitting down doing SD modeling, I don't know. What you usually find is there's one person here and there who does it, but not a big program. So it wouldn't surprise me if you name the university, they got somebody who does it, maybe even a couple people, but that's different than having a whole program where you can get a degree in it or take, you know, multiple graduate courses or what have you.
Right. Okay, that's interesting, because I feel like, you know, historically, it's very difficult to write policy that doesn't have like second, third order effects that are unwanted. So it seems like this would be a good way to help get ahead of those things. So I was just curious if that was useful.
Yeah, and that's where you get a counterintuitive behavior. You think it's going to work, but you get worse before better or better before worse, or you see unintended consequences of things and whatever. Yeah, exactly right. Yeah. And over time, so the unintended stuff might happen later. And you're not thinking about that sort of stuff. Okay, good question. So, but anyway, so you get the gist of you know, the demographic ideas here. There's a delay in acquiring skills, and we can try, there's some policy space in here if we accelerate through training programs, investing in training programs, speeding up people moving, through the educational or training process and getting a better paying jobs. So if you want to devote resources to that. And in the labor market, there's just various labor force participation rates and then unemployment rates among the folks in the various income classes. So it's not just the overall unemployment rate, but you can see within each of the income categories who's unemployed. The housing sector has upper income houses, middle income houses, and lower income houses. And look at the higher income is on the left and they move to the right, because as the housing ages, it typically starts to deteriorate and then goes to, you know, lower income categories. New middle income housing can be created or demolished, and same thing for low income housing. So this is kind of your urban renewal programs, constructing low income housing. And Massachusetts has a big push for that. They have all sorts of incentives for every town in the Commonwealth of Massachusetts to have 10% to build such that 10% of its housing is for low income people. And if you do that, you get points and you can get state grants and stuff like that. So you can do that over here. The big draw because what's our reference mode? The big draw for people to come to the city is the availability of jobs and housing. Those are the two things that are attractive, that lure people in. Okay, so when there's more houses here, that sends a signal that, hey, you know, of the type you can afford, you can in-migrate. You're a high income earner, you want a nice house, right? And if they're not available, it's less attractive. And then the other attraction is jobs. And so his models always reflected kind of a physical rather than a financial foundation. So what he said was the other thing that attracts people is jobs, but in his model and in the Urban 1 and Urban 2 models, the jobs are created by business structures. Okay, so you have new business structures mature and then deteriorating business structures. Okay, now notice for houses and business structures, there's a total area of the city, and once it's filled up, that's it. Now you can say the Japanese make artificial islands, and actually the city of Boston, the Back Bay was created. If you look at old maps of Boston, it didn't exist. They brought in railroad car after railroad car of fill, and they made the Back Bay in Boston. So you can expand the physical landmass of a city in some cases. Detroit is trying to go the other way, right, and shrink it, right? But the basic idea here, it's a fixed area in the city. So once everything's built on, you got to knock something down before you can build something new. All right. So the other key point to note here is look at this graph. Land fraction occupied. So as at the beginning of the evolution of the city, when very little of the city is built upon, the bias is blue instead of whatever that is, orange or whatever. So it's due to the land is used for businesses and jobs, okay, and less for housing. So the land that's used for housing is typically used for multifamily housing, row houses in Philadelphia, tenements in New York City, triple deckers in Worcester, multifamily dwellings, right? But they're available and there are jobs, so people start moving in. But once the city starts to prosper, look what happens. So this is called a table function. Well, this is from a couple table functions smeared together onto one graph. Once you get, past 40% or so, now the bias shifts because the city is starting to develop. You got upper income people and they don't want to live in a tenement anymore. What do they want? They want their own house with a yard and all that stuff. So the available land starts being biased towards single family dwellings.
Mike,
So
is there any way you could shift this screen? Because I think most of the graph is cut off, at least for me, the view. Is there any way you could drag your screen over to show the rest of that graph?
Mm-hmm.
Oh, yeah. Oh, thank you.
There we go. Okay, cool. So the bias then goes to houses, single family houses. So what happens? The upper income people and middle income people start moving out of the multifamily dwellings. They use up the land for single family houses instead of businesses. And so job creation starts to fall. And the multifamily dwellings they leave are occupied by the low-income households who can't afford to keep them up. So it starts to deteriorate and they become slums, right? And the people, but they're available. So people keep being attracted because it's houses and jobs. They're attracted by the housing, but there's no jobs. So they get trapped in the city. Okay, so that's the basic why the reference mode is the way it is. And if we run this thing, you can see again, qualitatively the blue and all that. It's not, it's a qualitative match. We didn't fit it, as I said before. Najla, yeah.
Oh, sorry. I mean, I know this is a pretty simple version of this, but like, could you add in like the effect of financial speculation?
Yeah, you could add in anything you want. Absolutely, sure. And there in this version, this is Al Feld and Graham's model, not Jay's. Jay had some financial stuff in there as well. Yeah, but I don't know if he had speculation. I don't think he had any speculation. But yeah, you
I
could.
was just thinking like with the housing sector in cities these days, that would dramatically, I would think, change the dynamics of the system if a city was targeted by real estate speculators.
Yeah, so the whole area of speculation is interesting, and that's positive feedback loops are involved with speculation. There have been other housing system dynamics models done. Some of them are very good. One was done by Jack Homer for the insurance business, looking at insurance rates in cities, which is a very good model. I'm unfamiliar with anything per se on speculation, but there's a research topic. But there are other system dynamics models of speculation, but I don't recall anything specifically in an urban model. But I could be wrong. Just because I haven't seen it doesn't mean it doesn't exist out there. Somebody might have done it. But all right. Anyway, so good questions. So that's the base run here, right? Now, again, we're just trying to tell the story of system dynamics. So we don't want to this is not a whole urban dynamics course, right? So we have to cut it off at some point here. The point is that this is when it switched from industrial dynamics to system dynamics because Jay went beyond corporate modeling. So that's when he said, we're going to call it system dynamics, number one, because now we're doing sort of social system modeling, or public sector centric modeling or whatever. But also remember, we said you have to define what better means or what the problem is or what have you. So just for giggles, let's just use the unemployment rate for lower income people. And as you can see here, at the end of the run, it's 22.6%. It's peaking around 23.8, 23.9, call it 24%, quarter of the population. So let's use that as our scoring metric. There's a whole lot of things, but let's just for quick illustration purposes. So let's do an education program. Let's turn it on and let's move people into higher income jobs much more quickly. Completely successful education program, and let's see what happens. So we'll call this first one here that we just ran before we run it again. We'll call this one the base run. So this is the base run, and this will be our scoring metric. Now let's run it with a perfect educational program. How'd that work out? It's the same. Didn't do anything because of all the feedbacks in it. Now you can hunt down exactly why, we don't have time for that, but let's turn that off. So we move people over right quick. It didn't do absolutely, in this model, it didn't do absolutely anything. You might say that's a little weird. Maybe it should have done something, but it's not my model. So anyway, okay, so let's try the controversial thing, which was instead of building low-income housing, let's knock it down and make room for businesses to create jobs. What happens now? So as you can see, the low-income folks have a way lower unemployment rate by getting rid of the slums, knocking it down. Now, there's probably going to be some displacement of people that the government have to take into account, whatever. But it's counterintuitive. LBJ and the urban activists want to build low-income housing for the poor. Jay is saying, knock it down. Yeah. Can see where Jay said, you know, Jay was fearless. Somebody would come after him, an activist or whatever. He'd say, come to MIT. Come on. Let's talk. Let's do a seminar. And he said after the first day, he'd come crawling out of there. He says after the second day, they were all urban dynamicists because they had finally understood the model and why things were happening. All right. We could go on and on and on with this stuff, but you guys get the idea here. Okay. What's my clock doing? Oh, we got time. All right. So, where is my thing that says clear? Here we go. Clear frame. That's what I wanted to do. All right. So now, J, I got to find the spelling here on another screen because I always spell it. I'll get the name right. Sorry about this. I never get it right. Aureliopeccei. Aurelio Peccei. Okay. So what's going on with Mr. Peccei? So Aurelio Peccei was a Italian businessman. Let's see if we can just quickly put him in here. And he was a very interesting guy, very successful businessman. He was a war hero. He led the Italian resistance or some of the Italian resistance during World War II. And in the 1960s, he became alarmed by what he called the predicament of mankind, or it's also called the world problematique. So Peccei created an organization called the Club of Rome. In what city was that club organized? That's a joke. That would be Rome. When did the War of 1812 start? Who's buried in Grant's tomb? At any rate, the Club of Rome was devoted to the predicament of mankind, or the world problematique, which was, Peccei said, we the club notice that the world's population is growing and growing exponentially. And as a consequence, it's using up its natural resources at an exponential rate, and it is generating pollution at an exponentially growing rate. And this is bad. In the future, bad things are going to happen if we keep chewing up our resources and creating pollution. So this is the world problematique, the predicament of mankind. And he was doing this in the 1960s. Now, today, we're concerned with climate change and sustainable development and whatever, but this guy was doing this in 1962, right? So Peccei hears about the urban dynamics stuff. And he invites Forrester to an urban dynamics conference or a city conference, or maybe, I don't know if they invited him or they met, whatever. My memory's a little unclear about that, but at any rate, they met. And Peccei says, if you can model a corporation and if you can model a city, can you model, to Jay, the predicament of mankind? And Forrester said, well, maybe, yeah, probably, I don't know. So the Club of Rome invited Jay to a meeting in Bern, Switzerland. And they asked him, explain system dynamics to us, and he did. And then he said, well, explain the world problematique, the predicament of mankind, to me. And they did. And at the end of the meeting, they agreed that they would fund Forrester to build a system dynamics model of the predicament of mankind. Okay. Now, Let's see. What time do I got here? I got a little bit of time here. So this begs some important questions, and this is a big part of system dynamics history. And if anybody knows anything about system dynamics in the general public, academics or whatever, they're going to know about this. They're not going to know about SAGE or Whirlwind or even urban dynamics, but they're gonna know about this world dynamics, world problematique thing. So the question arises, is economic growth always a good thing? In my field of economics, it's a given. Of course it is. It's a rhetorical question. Can technology solve all socioeconomic problems? Well, technology has always served us well since the Industrial Revolution. You're running out of food, invent better seeds, invent the plow, and so forth, and problem solved. So are there really any limits to growth, or does technological innovation always push out the limits to growth? There's your world population growing and growing exponentially. Exponential growth, as you'll see, is both powerful and insidious. It sneaks up on you, right? We're going to see a clip maybe next time, so I'll show you what I mean by how it sneaks up on you. But anytime you see this time shape, it's very powerful exponential growth, and a lot of over certain time scales, it looks linear, right? But real systems grow exponentially, not linearly. Here's global GDP, the world's production of stuff, if you will. And even if on a per capita basis, it's growing and growing exponentially. And more specifically, here's plastic production, water demand, energy consumption, material extraction, materials in use, fertilizer production, meat production, seafood production, food demand. But look at this, arable land is going down. And pollutants are being generated, plastic waste, material use and pollution, various kinds of pollution, global emissions, CH4, carbon dioxide. So the question is, what's going to happen here, right? So the nations of the world actually started paying attention to this in 1992 with the Earth Summit in Rio de Janeiro. The nations of the world gathered and they signed Agenda 21, the agenda for the 21st century. That was precipitated, I think it was 1988, by the Brundtland Commission. Gro Brundtland, the Prime Minister of Norway, led a commission, I think for the UN, to define what it meant by sustainable development. Essentially, it's the interaction of the economy and the environment. That's the traditional definition of it. We're going to look at something that Herman Daly, an economist, he just died. He was 84. He passed away last year. But he had a nice definition of sustainability that I like. Layla, I have her up here. She wrote like a 35-page paper where she was surveying all the different definitions of sustainable growth, sustainable development. And it's like, hey, there's no consensus here. Brundtland basically said, you don't want it, whatever you're doing today, don't wreck things for future generations. That's essentially what, if you're going to live sustainably, what that means. And you could go to the link if you want to read about it. So you get into sustainable growth versus sustainable development. So the argument is sustainable growth is impossible because systems have limits. But sustainable development is possible. You can make the system of higher quality, but not bigger. Okay. So think of a library, it might have shelves for 1,000 books. Once you have the 1,000th volume, you can't have anything more. You can't grow your library, but you can take outdated volumes out and put newer volumes in and improve the quality of your library. You can develop it. So here's Maya to make a diagram of sustainable development, the world problematique. You have the economy in blue, the government sector, the public sector, and then the private sector, households and firms, they all interact. And in order to make stuff, you need resources, renewables and non-renewables. So you have to extract them from the environment. And in turning the resources into things, you generate pollution. You have to, or you violate the laws of thermodynamics. If you think you can, not generate pollution, it doesn't happen. And the pollution gets expelled into the environment, the land, the sea, and the air. Okay. So in light of that, what do you do so you don't wreck the environment? Old idea in economics, it goes back to the classical economists, including Malthus here. I'm looking at my clock here, we got time. So Malthus wrote a book. I got it on my shelf here. Let me quick see if I can grab it. If I got to search, I won't do it. So here it is. Thomas Malthus, come on now. An essay on the principles of population, right? You can see that's how I used to do system dynamics and IBM punch cards. I use them as bookmarks. See, you punch the holes. That's one line of system dynamics code right there. So let's see if I can. So here's what Malthus was saying back in the 19th century. I think I may fairly make two postula. First, that food is necessary to the existence of man. Secondly, that the passion between the sexes is necessary and will remain nearly in its present state. Okay. Well, he has a whole book on it, but that's the gist of it. Is like food grows linearly, but people grow exponentially and they demand the food. But at some point, so Ricardo talked about the law of diminishing marginal productivity, and he thought about agriculture. So as the farmers grow on the best land first, and then on the next best land, and the next best land, and then they get to the rocky shore, and then they get to the water, and that's it, right? So Malthus was going, look, population is growing and growing like hell, and the food is not. So he predicted all these terrible things. And he was also a reverend. A lot of the Cambridge dons, he was an economist at Cambridge, the first economist at Cambridge, but he's also a reverend. And so, making babies was good. The Bible said so, right? So it's an old idea. So here's some stylized graphs. The economics profession, remember, I keep circling back to economists because what's the first paper in system dynamics? He's taking a shot at the economists, right? So look at here. This is what you're taught in economics graduate school. The carrying capacity is supply, food, if you will, whatever, just general carrying capacity. And the stock is demand. So the demand, people are growing exponentially, but the carrying capacity is growing exponentially faster than the demands on it because of technology. So we're all good. That's why you're taught this in econ class, all the econ classes. That's one extreme. The other extreme, if the pendulum swings the other way, you have a fixed carrying capacity in green in the upper right. And in this case, you have exponential growth like you do here. But as you start to approach the ceiling, it starts to slow and you smoothly balance supply and demand on the British Isles or in the global scale. If you exceed the carrying capacity, one of two things can happen. You can oscillate around and get to it. And by the way, when the red line is going down, bad things are happening, or you can kill the system and really bad things happen. Okay, so those are just stylized, but here are some UN predictions, and you can see 3 of the 4 graphs are the UN is saying it's going to be one of those 3. We don't know for sure, but it's going to be one of those 3. So there's Jay looking at Malthus. There's Jay at WPI. He's back at WPI. We're doing whatever he was doing with us. I can't remember. More Jay stuff. All right. So how does Jay model the world problematique? Well, all the world models, made by Forrester or others, or not even, SD people, basically have these sectors. People, okay, people need food, right? Pollution hurts the food production. People want things, so you need natural resources, and they're used in, with machines and so forth to make things, which also generates pollution. But if it goes to the population, and the natural resources are also used for agriculture. So these sectors all interact. So on the plane ride back from Bern, Jay said, oh, by chance, the back of the plane was empty. So I just took a whole row and made myself an office, and he was working on conceptualizing the model. And here's what he came up with. This is literally what he did on the plane back from Bern. And we call this World 1 in our field. So, stocks and flows are here. Notice we got population, population, right? And then he has a net birth rate here. He had a death rate, and then he scribbled it out. Or wait, there's a death rate over here. I don't know what he was doing. I just noticed there's a death rate here. Okay, births and deaths. Okay, cool. Capital investment, pollution. Where's pollution, right? Natural resources, and agriculture is here. Here's land, something or other in here. Well, you got, it's hard to see his writing, but he's got land, and he's got the agriculture in there as well. He got back to MIT, and he turned this into this, and that's World 2. So what Jay said was, well, I have to write this up for the Club of Rome in a document, show them the model. So I have a manuscript. I'll send it to be published. Professors publish, right? So he sent it to a publishing house, but it had only published one book prior to him sending it in. It was a very small local publishing house. And he figured, beyond the Club of Rome, a few ecologists and whatever, maybe a few economists might be interested, but nobody will really care. But what the heck, I had to make a manuscript anyway. The book became an international bestseller. And Jay said he was absolutely flabbergasted at that. He said it was reviewed on the order of by 5 major publications on average per week in the first year of its publication. He said he got calls from people saying things like, I was just reading about, he wrote it up in a book called World Dynamics. He said, I was reading a review of World Dynamics in the Singapore Times today, and blah, blah, blah. Jay used to joke that in terms of the spectrum, the book was reviewed seriously and at length in both the Christian Science Monitor and Playboy magazine, if you can imagine that. Playboy magazine devoted an entire huge section to reviewing the book in a serious manner. He said he was absolutely flabbergasted by this. Okay, now, once again, the book is controversial because it contradicted a lot of what was taught in economics. The economists didn't care about his memo, right? As I mentioned, the MIT economists and whatever. When he did urban dynamics, a few economists who worked in the subfield of urban and regional economics cared. And for example, they would beat him up over, there's no suburbs in your model, so your model's crap. Now, Jay lived in Concord, Mass., a suburb of Boston. He was aware that cities have suburbs, but it was not part. Remember, you draw a fence. You only put the important stuff inside the model, right? Important to the problem. He didn't think the suburbs were. But he got so much grief about that. He said, fine. And he got a master's student to take the urban dynamics model, tune it up for Lowell, Mass., and then add the suburbs. And none of the policy conclusions changed at all. Now, the book was controversial because of this. The basic behavior was overshoot and collapse like the urban dynamics model. And that contradicted everything that was taught in macroeconomics. Okay, so now the economists are paying attention. And for that matter, on the plus side, lots of people were paying positive attention. And the Club of Rome got a little nervous. They said, we know you're a smart guy, Jay, but you did this thing on a plane ride refined it in 3 weeks. You model the whole world. Like, why don't we give you more money and we'll fund a team to help you redo it? We'll fund demographers to help you do the demographic sector. We'll fund agricultural specialists for the ag sector, et cetera. And let's redo it to make double sure we're more than delighted. We wanted attention to the world problematique. Oh my gosh, did we get attention? Jay said, I can't. I'm responding to all the critics of urban dynamics. But I'll tell you what I'll do. I'll have my former doctoral student, Dennis Meadows, redo the study. And Dennis can hire a team and whatever. And they said, okay. So Dennis pulled together a team. First person he hired was his wife, Donella Meadows. She was a biophysicist and a system dynamics modeler, but she was a super, super talented writer. And they said, Jay's books are equations and graphs and stuff. Let's write, when we present our version of the study, the team version, let's get rid of all the math and the equations or whatever. We'll put that in a separate book for the people who want to reproduce everything. But let's write for the common citizen. So let's get rid of all the technical details and just tell the story. So Donella was asked to write the book, and she did that. And that book was called The Limits to Growth. So Limits came out in, I think Limits was 1970. It's either 71 or 72. I don't remember. And that was, so Jay's book was World Dynamics. That was 1970. And then that was followed by, I think that was 71. Okay, so when Limits came out, Jay said, nobody's gonna care. Everybody saw my book. So everybody knows it's just sort of the same message. No biggie. Now, the model was more sophisticated. Notice there's these boxes with these little compartments represent delays. They kind of look like stocks because stocks create delays. So delays are special stocks. Okay, so there's more going on in the model. There are different population groups. There's delays before pollution impacts the environment. There are different types of land. Land is used for different things. So it's a more sophisticated model. There's delays all over the place here. But it was kind of the same story. And Jay said he was flabbergasted again when The Limits to Growth became an even bigger international bestseller. It's been translated into, 50 different languages. Queen Juliana of the Netherlands personally presided in its presentation to the population of the Netherlands. It was unveiled at the Smithsonian Institution. It was, to this day, the phrase "the limits to growth" is quite well known in ecology, economics, social science, and what have you. Okay, so what did Jay say? I'm looking at my clock here. We're doing okay. I don't know if I'll finish everything tonight, but so let's talk about what the message was in both The Limits to Growth and World Dynamics. So here's the standard run. And notice they purposely took all the scaling off the vertical axis because people freak out with big numbers and stuff. Let's not worry about that. There's a technical book if you want to worry about that. Let's focus on the message. But they said where they had data, they made the model mimic the data. And then they said, let's run it out into the future to the year 2100, assuming nothing changes. And look at what happened. Around 2050, the world's population collapses, not to zero, but this is on the order of billions of people. What's the problem? Natural resources run out. Okay. Now, what Dennis and his team said, and Jay has similar arguments. You're going to play, by the way, you're going to play with the World Dynamics Simulator, which you can run all of Jay's stuff and some other things we'll get to today or next time. But at any rate, they said, but nobody's going to sit on their hands and watch the world collapse. So when it becomes clear that this is a problem, resources are running out, let's assume smart people are going to recognize the problem, work on the problem, solve the problem. Okay, so let's put that change in and let's see what happens. So here's the world model with unlimited resources. Basically, they said nuclear power is going to allow much more recycling and substitution and whatever. And looky what happens. The system collapses, even worse than before. What? Notice natural resources are fixed. That problem has been addressed. And now pollution goes through the ceiling. And they said, well, smart people fix the resources problem. Smart people will recognize the pollution problem, work on it, and let's assume they solve it. And let's keep the resource solution as well. That should fix everything, right? So here's the world model with unlimited resources and pollution control. So pollution has been fixed, and natural resources, they're a little lower, but they're still, they're not going to zero. They're leveling out here. What happens? The system collapses again. What's the problem? Run out of food. Okay. Let's assume smart people will notice that that's a problem, work on the problem, solve the problem. Let's keep the pollution and natural resource solutions from before. We should be good to go. Nope, system collapses again. What happens? Pollution goes through the ceiling again. How is that possible? Well, they reduced it, the unit of pollution per unit of GDP to 1/4 its 1970 value. And you can't make it zero, or you're violating the laws of thermodynamics. They made it 1/4. You can make it 1/5 if you want. You can even try that in Jay's model. But it released so much growth that even though each unit of GDP was producing much less pollution, there was so much growth, pollution went through the ceiling. It's as though you have smog in Los Angeles, so you put catalytic converters on the tailpipe of every car, but then you double the number of cars in Los Angeles. You have the same amount of pollution. So they said, really what the problem is people. There's too many babies. So what if we add perfect birth controls? Better, right? It's looking like we're stabilizing here, but then, so what's the final fix? Value changes. If you get people to value services and leisure above things, not entirely, but more so, you can stabilize the system in a very nice way with a world GDP 3 times the average in 1970. But then they said, we started having people, they were doing this in 70, 71, 72, and in the simulated year 75, they said, let's have people start to pick up on the problem and solve it. Not instantly, but I think it was 20 years to solve it. They said, let's assume people aren't going to pick up on the problem and do anything till it gets really bad, because that's what people do, right? Which was the simulated year 2000. Try all these policies, but starting in the simulated year 2000, it's not sustainable anymore, because it's like cancer. If you catch it early, the exponential growth of the cells, you can save somebody, but at some point you can't get it all, right? It's like, because it's exponential growth in a finite world. Sturman will always say it at MIT, if you're driving down the road at 100 miles an hour and approaching a hairpin turn with a cliff, if you wait too long to get on the brakes, you can stand on the brakes and you're still going over the cliff. You've waited too long, right? All right. So where's my clock? We're just at time out here. This is kind of a natural place to stop. Next time I'll wrap this up and I'll tell you how I got involved, because what happens is the economists went after Jay like crazy, and the system dynamics people like vicious crazy over this thing, because now he's playing on their main turf, macroeconomics. Okay. And Jay fought back. And this was in the 70s, when for the first time in the 20th century, we had stagflation, the simultaneous occurrence of both high levels of involuntary unemployment and high levels of inflation. Now, we didn't have macroeconomics until 1936. And really, it didn't get rolling till after World War II. So macroeconomics didn't exist very long. But the macroeconomics that existed in the 70s said inflation is an overheated economy, involuntary unemployment is an underheated economy, but we had both. How can you have an overheated and an underheated economy at the same time? And Jay said, oh yeah, you guys are picking on me and you can't even explain what's going on here. So Jay decided to build a system dynamics model of the US economy. He's not backing down from the economists. And that leads into how I got involved with system dynamics, being an economist and so forth. So we'll save that for next time. But let me show you one last thing before we all go and do what we got to do for the rest of the day. The next, and I need to put these links where you guys can see them if you're not have access to Canvas. But you can run Jay's model here. So again, just real quick, because we're out of time here. Again, the template is the same. You can look at the model structure. So here's the demographic sector of Jay's model, quality of life. And one last thing I'll call your attention to, Jay's model does not have an explicit technology sector, okay? Remember, the question is, can technology always save us? Well, Jay said, well, it's embodied in the plant and equipment and whatever in my model. Well, Robert Boyd, a zoologist out in California, said, this is, I'm going to redo Forrester's model, but I'm going to put in a technology sector. And let's see what happens. So you explore the model structure, and when you go to here's what you can run. I'm doing this fast, but you can see down here, you can turn on Boyd's technology policy, and you can turn it on at different, whatever year you want to start the policy change. You can follow Jay's, I tell you, you can run his simulation experiments. This is from the book. He tells you do this, do that, do this, do that, right? So, and then you can try to do the Boyd thing and see what Boyd had to say about it, right? And then you can play on your own. You say, well, why start at 1970, whatever, let's try it in different years and what have you. Okay. All right. Oh my goodness. How we doing? Bored out of our skulls, or do you think this is worthwhile, getting the lay of the land, the narrative behind the field?
I love this. To me, it's like watching a soap opera.
Yeah, most people find it very interesting. Yeah. So sorry, go ahead.
I just said I think it's very interesting too. I mean, it's just a interesting history, and obviously it's still very relevant today. We're still talking about pollution and what that's going to mean. So it's interesting that conversation started so long ago.
So, okay. So anyway, so we'll wrap up the limits story, because there's a few more things to say about it. Then we'll go into the national model and the stuff that was done there. Some real interesting stuff, super interesting. And then I'll give you a peek at the future. Jay concluded, when they were beating him up over a little bit about urban dynamics, a lot with world dynamics, a lot with the national model, he concluded, as did Sturman and his other staff, economists hate system dynamics. And I show up, ding, 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 ding. I'm an economist. Some economists will hate system dynamics, but some economists would like it. You got to talk to the right economists in the right schools of thought. None of those guys were trained in economics. They had no idea there were schools of thought in economics. And I convinced Jay he's got to talk to the right economists. And so that's how I got involved in all of this stuff. So we'll save that for next time. Okay.
What would be fun would be to have another version of this and have Jim Hines also participating in. I've heard a few of these stories from him on the original system dynamics course that was taught by Oleg Pavlov, and they used some of those old video tapes of the Jim Squared.
Jim Squared, Jim Hines, yeah. Linus, yeah, the two Jimmy.
And he's hilarious. And then I've seen some other clips of him, like at old SD conferences and stuff, talking about, how bold and how outspoken and just completely unflappable that Jay was when he got older and he got invited to these conference and stuff, and he would just blurt things out and offend everybody. And he'd walk back and tell Jim Hines, now they won't invite me back again next year. I won't
Yeah, he
have
would
to
say
do
stuff
this."
like that. Yeah, he was fearless. He backed down to nobody. But he was so smart. I mean, he wouldn't, but he was not a yeller and a screamer by and large.
No.
Few times I saw him, kind of, but by and large, he would just say, well, and he'd go boom, 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 but he would never back down. Absolutely not. He was,
Yeah,
and you
Jim
better have
Hines'
your-
interpretations of Jay Forrester are absolutely hilarious. Super
everybody did
funny.
impersonations of him. Well, everybody put their hand here. Well, and then the pause. There was always a pause. You'd be like, when you first met him and you'd ask him a question and he'd pause, you'd be like, why is he pausing? Why is he not speaking? Do I got spinach in my teeth? What's the problem here? But he was thinking. And then he would give a thoughtful answer. He wouldn't just blurt out that, but it's all sorts of crazy. There's a million Jay stories. Some of them are not repeatable here, but but a lot of them are kind of funny and, different.
So you're going to make all that
interesting
stuff.
cat,
Yeah. Oh, very, very much so. So you're going to make some of those models available in our little folder on the Google
That's
Drive.
what I said earlier. Look and see what's there. I
Okay.
uploaded everything I had from my SD550 files. But as I mentioned, I'm sort of redoing it for the Trending Cycles Thinkific site. And I've changed some of my mind and, so they might not be identical. So if there's something that I've shown or talked about, but it's not there, it might be because it's in the other one and I didn't realize, and there's a lot of files, so I didn't take time to go everything line by line. But as things unfold, if something's missing, like you talked about this or you showed us this and it's not there, let me know. I'll find it and I'll upload it. And the other thing is, just FYI, not everything is in Stella yet because I haven't translated everything yet. So it's in Vensim, so you'd have to get a free copy of Vensim PLE.
I think I have that on my computer, but I do hate Vensim.
If you desperately want to open a file and look at it, because it's not yet in Stella, you'll have to get Vensim.
Okay.
So, but I emptied out whatever I had and uploaded it to the Google Drive, and I'll put today's talk on the YouTube channel. It takes a while to convert it. So it has to be converted on my machine, and then when you upload it to YouTube, it has to be converted. So there's some IT thing that happens, and it's not a fast thing. It's several hours in each case to convert it. So I go and do something else, or I go to bed.
Because
the next
it's
day,
long. It's 2 hours, yeah. All right. Well, thank you very much. Same bat time, same bat channel next Monday.
Oh, okay, sounds good. And I'll see. I need to put up these links to the flight simulators because they're obviously in the Canvas thing, but I don't think I have a listing of them in the Google Drive. So I'll have to put up like a PDF with the links or something. I'll figure that out. But okay.
Okay. Thank you. See you next week.
All right. We'll see y'all. Take care.
Bye.
Bye.